Welcome, welcome, welcome. You guys are ambitious. Oh my goodness. This clip is an extension of the previous one with Q, where we found if I had, what is it, 9 A's, A2's, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 8 B's in an equilibrium with 5 AB molecules, that we thought that actually we're given the equilibrium constant of 10. Which way will the reaction go? Is this reaction currently at equilibrium? Did a little calculation. We found Q to be 0.347. So the reaction quotient, the comparison, the classic convention to say how do these reactants compare to these products. Again, we came up with 0.347, which is much smaller than the 10. So if that's smaller than, so if Q is smaller than K, then I know this is too small, and or this is too big. This is too big, and or this is too small. So in other words, I move toward the right to form more of this stuff over here, so that Q grows up, in a sense, in a manner of speaking, to be equal to 10. And it happens also incrementally, also slowly, to say it grows from 0.3 to 0.4 to 0.5 to 0.6 to 1 to 1.1 to 1.2, all the way up to 10. Then the reaction's at equilibrium. But the question is next, and we'll practice more with this in the weeks to come. The question is this: if I had this equilibrium, my constant is 10, describing the proportionality, the partitioning between the two phases. How can I go about figuring out what I'll have in the end? I think I had 9 of these, 8 of these, and 5 of these. How much will I have? We could call them 9 million, 9 quadrillion, 8 quadrillion, and 5 quadrillion of those. When I finally reach an equilibrium, where will that lie? How much of each will I have? Here's a classic table that's used. It's used all the time. Almost every textbook you'll ever see breaks this table out, or a table like it. Some of them break it out earlier in talking about stoichiometry, but we're going to use it especially when we talk about equilibrium here. And we have an initial condition. We have something that changes. We have an equilibrium. Interesting. The first few times you see this, it's really a little tricky. So here's my initial state. I had 9 or 9 quadrillion, 8 or 8 quadrillion, 5 or 5 quadrillion, or make up any number you want, any unit you'd like, but it works. So we just decided that we were going to move to the right, so these are going to come together to make more of this, because the constant was 10 and my quotient at this point was 0.3 something. So these two are actually going to react to make some of that. So guess what's going to happen to the 5? It's going to go up. Guess what's going to happen to the A and the B? A2 and the B2, they will go down. But I do not know by how much. So what do I say? I say, well, this is going to go down, and this is also going to go down. And since there's a 1 in front here and a 1 in front here, they'll go down by the same amount. This will go down by the same amount except for the 2. So one of these and one of these create 2 of these. So because of that 2, I'll put a 2x here. This 5 will increase. So really all I have to do now is figure out what x is. Psh, that's all. Easier said than done sometimes. So what do? I say 9 minus x. I say 8 minus x. I say 5 plus 2x, and I still don't know what x is. But you know what? I do know that the relationship between this squared in the numerator and this multiplied times this concentration in the denominator must equal my constant. And you know what else? I have found the constant. Or I should say, yeah, we determined it earlier. Excuse me. So I have an expression from the mass action, law of mass action, or the definition of equilibrium constants. And then I have some numbers to plug in. This is 10, and I have all these relationships, but I still don't know what x is. Well, if I FOIL this, numerator and denominator, I get this. First outer enter last from math, you know that? Remember that? Anyways, now I'm getting a little bit scared. This is called what's called a quadratic. To help solve for it, I'll multiply both sides times this denominator to bring it over to the 10 side. Distribute the 10 into the parentheses, and I get 720 plus 10x minus 170 x. Then on this side it remains the same, and unless I made a mistake, I hope I didn't. I'm sure he'll let me know if I did. I subtracted the 4x squared from this side over to this side. I brought the 25 from this side over to this side. 720 minus 25 is 695. And I subtracted the 20x from this side over to this side, creating... No! Did I make a mistake? Let's see. If I subtract 20x, that'll give me negative 190x. Alright, pause. Sorry, I'll be right back. Oh, goodness gracious. I had to go fix that because it was bugging me. And not only that, all my other calculations or illustrations hinged upon that. Anyways, subtract 20x from this side over to this side to get negative 190x. Then we think back to our junior high algebra skills. I think is actually when this was first taught. It's a while ago. It's called the quadratic formula. To solve an equation in x squared and x, you set up, let's say this is the a term, this is the b term, this is the c term, and it's negative b plus or minus, so there's always probably two answers, maybe not real, but in any case imaginary if the square root ends up being a square root of a negative number. And I put the 6 in the a's, and I put the negative 190 in the b's, and I put the 695 in the c's, and I chug out an answer. The plus or minus is, of course, because there could be two different answers. 190 plus this term, 190 minus that term, both divided by 2a. Solving them sort of separately, I see 27 and 4, 27.4 and 4.25. So they're both answers, but if I think about the graph, or look at the graph, I will remember what the solution to this quadratic looks like. It's a parabola, and we're asking what the roots are when the parabola crosses the x-axis. 4.25, 27.4, but you know what? I decided this was too big, or this answer doesn't make any sense, because of the following. If I remember back to my equation, or my relationship, if I tried to put 4.25 in any of these, I would get a reasonable answer. But if I tried to put 27.4 into my original quantities, 9 minus 27, 8 minus 27, those give negative amounts of these chemicals. And you can go to 0, theoretically, but you can't have negative amounts. That's how I decided that one root of that quadratic was too large. Then you go ahead and go back and put the numbers in. Put x, for x, put 4.25, 4.25, 4.25, everywhere you see x. Solve for the solution, solve for the amounts. So A started at 9, goes down to 4.75. B started at 8, goes down. And AB, the molecule, B2, A2, AB, went from 5 up to 13.5. And if I were to look at a graph of that, it might look something like this, where A and B come down together, A2 and B2 come down together, both plateau after a certain point, and that certain point called the equilibrium. And the molecule AB increases twice as fast, but still flat lines, plateaus, equilibrates at that same time. As the forward reaction slows, the backwards reaction picks up, and I find an equal place in the middle. Oh goodness, see how that sits, and we'll practice that some more in probably on OWL, probably on suggested in chapter questions in class. Thanks guys, see you soon.